All right, so let's jump to question 1. So we're looking at simultaneous linear equations, and we're just going to use trial and error to figure out which set of linear simultaneous equations match this set of matrix equations. So I'm just going to go one by one. So let's look at what would the first equation be. So if you think about this in terms of matrix multiplication, your first equation will be 2 times v. So we're going to have 2v plus 2w plus we've got 0 times x. So we're not going to bother with the x component. And then finally we've got negative 2 times y. So it's actually minus y. And that equals 2 because that's our first element here. So that's going to be our first one. So I put that in words so it's a bit easier to see. Now let's get the next one. We've got 2 multiplied by v, nothing by w, then negative 2x, and nothing with y, and that equals 6. So we've got 2v minus 2x equals 6. And we can just keep doing this. So 0 with v, 2 with w, 0 with x, negative 2 with y, and that equals negative 8. And finally, we've got 2v plus 2w minus 2x, and that equals 4. So now we're just going to see, that's our system of linear equations. We're going to see which one's which here. So if we just sort of go through and compare them, we will get B. So B is the one that matches this one perfectly. So B would be our answer. Next multiple choice question. What is the order of this matrix? Now, if we think back to our notes, when you're listing the order of a matrix, it is the rows times columns. So rows always comes first. You can see we've got 3 rows here by 2 columns. So it's going to be 3 by 2, which is answer B. If A is a 4 by 3 matrix and B is a 2 by 4 matrix, what will be the order of the product matrix of these two matrices that is defined? So this question is actually a bit tricky. So it hasn't actually specified whether you're finding the order of the matrix AB or BA. It doesn't actually specify it. So let's check both. So let's check AB. When you're multiplying A by B, you've got a 4 by 3 matrix multiplied by a 2 by 4 matrix. Now, if you remember back into your matrix multiplication notes, in order for a matrix to be defined, the two middle numbers need to be the same. So the number of columns in A needs to be the same as the number of rows of B. And in this case, that's not the case. So AB is actually not defined. So let's check out BA. BA is a 2 by 4 matrix, and that's multiplied by a 4 by 3 matrix. So because the two middle numbers are the same, BA is defined. Now, how do we know what is the order of BA going to be? Well, it's actually going to be the two outside numbers. So it's going to be a 2 by 3 matrix. You just sort of take the two outside numbers there. And if we check our notes at 11D, looking at the product of matrices, we see that this is where we find it in the notes. The two inside numbers are equal. Therefore, in this example, AB is defined, and it's got a order of the two outside numbers, so 2 by 2. So in our case here, BA will be a 2 by 3 matrix, which is option C. Multiplying the matrix M by 5 will do what? So what we're doing here is, or what the question wants you to acknowledge is that 5 is just a scalar number. Right? It's just a number on its own. It's not a matrix. So if you can recognize that, you might go to scalar multiplication. So if you want to say find 3a, for example, where you're multiplying 3 being a scalar by a matrix, what you're actually doing is you're just multiplying each individual element of A by 3. So if we look back to our options, we're obviously not increasing each element by 5, because that would be you're adding 5, not multiplying. We're not raising them to a power. It's not the product of a 2 by 2 matrix filled with 5s. And it is D. It is multiplying each element by 5. So that's what it is. But a public library organized 500 of its members into 5 categories according to the number of books each member borrows each month. We've got these 5 categories here, and the transition matrix T, this one here, shows how the number of books borrowed per month by the members is expected to change from month to month. What the question is asking is, in the long term, which category is expected to have approximately 96 members each month? So the key here is in the long term. So quite often when a question is, it wants you to calculate the steady state solution, it'll use the wording in the long term. So we know we're going to be looking at steady state solutions. So let's have a look at what our notes say about that. All right, we've got steady state solutions. So essentially the rule, what we want to be doing is we need to get our initial state matrix S naught and multiply it by t to the power of n. And the steady state will be as n tends towards infinity. So what I tend to do is maybe you'll work out S10, so t to the power of 10, and see what that does. Then try 100, then 200, 300, until you sort of start getting a steady state. So obviously the first step here is we need to get this matrix into our calculator. All right, so we've got that in our calculator. Now, the next thing we need in our calculator is the initial state matrix, which is going to be a column matrix with 5 rows, because we've obviously got a 5 by 5 transition matrix. Now, this is where it gets a little tricky, because it doesn't actually tell us. It does say we've got 500 members. That's important, but it doesn't tell us initially where they're sorted into. So we don't know the initial state matrix. So maybe I'm just going to take a guess and say that they're sorted evenly between each of them. So let's say this is S0. Oh, all right. Now what we can do is let's work out our steady state here. Let's try with 10. All right, you can see we are looking for the category that's expected to have 96 members. We've already got a number that has 96, but let's try 100 to confirm that this is actually our steady state. Yep, 96 again. So the fact that it hasn't changed between 10 to 100 steps, that makes me assume that this is our steady state matrix, and category K, because see how this is the second row in our steady state matrix, and K is the second row here. So that would be K. All right, but what if they weren't distributed evenly? What if, let's say, at the beginning, all 500 members were in one of the groups? So what happens there? So if I redefine S0, it's automatically going to redo this calculation as well. And we actually got the exact same steady state matrix. So that's actually an interesting fact about the steady state that wasn't mentioned earlier. It actually doesn't matter what your initial state matrix is. Let's try something else. Let's try 200, 100, and another 200 there. Let's see if that changes our steady state matrix. No, again, the exact same steady state. So that's kind of the point of a steady state matrix. It doesn't matter where you start off. This transition matrix will eventually tend to the same steady state. So no matter how you organize your initial state matrix, category K is going to end up with approximately 96 members. So our answer for that would be B. The matrix equation below represents a pair of simultaneous linear equations. These simultaneous linear equations have no unique solution when m is equal to what? Now, because this is a multiple choice question and we actually have options here, there are a couple of ways you can approach this question. One way is to simply do trial and error. So if we remember back to simultaneous equations, what happens is if the determinant of A equals 0, then you have no solutions. Yeah, and that's what we're trying to do. So when the determinant of A is 0, you have no solutions for your simultaneous equations. So if we can find the value for m out of these options, when the determinant is 0, then that's going to be our answer. So we can just use trial and error. That's one way to do it. Let's try our first option, -4. All right, that's not 0, so that's not going to work. That's not 0, so that's not going to work. Nope. Nope. Yep, finally. So the only number out of these ones for m was 4. That gave you a determinant of 0. So that's how you get your answer E. The other ways you could do it, I personally think this was the best and quickest way to do it. But you may notice for working out the determinant, there is actually this formula. So you could sort of use the formula and try to work backwards from there, but that is a bit tedious, probably takes a bit more time, and uses a bit more brain power than just using this trial and error method. So this is your go-to. So we've got this matrix M, and we want to find the rows or the sum of the rows of M. So we're trying to find the sum of these rows. So what we're going to end up with is, if we're finding the sum of row 1, row 2, row 3, we're going to end up with a 3 by 1 matrix that has the sum of each row. So it's going to be a 3 by 1 row column matrix. That is going to be our product. We do have notes about summing rows and columns. So let's check back with them. They're fairly early on from memory. Here we go. Summing rows and columns. So this is another important point as to why I've sort of made these miniature headings. Maybe not 100% of the time, but a lot of the time, the important information or the sort of the important topic that you're looking for to answer a question is defined by these headings. So they can be really handy for pinpointing the information that you need. So if we want to find the sum of the rows of a matrix, we post multiply the matrix by a column matrix filled with ones. That's exactly what we want to do for this question. So we want to post multiply by a column matrix filled with ones. So a column matrix is a matrix that has 3 rows and 1 column. So we're post multiplying M by a 3 by 1 column matrix filled with ones. So option B here. All right. Now this is just a transpose question. So the transpose function in your CAS is just TRN, and we can just pop it straight in. So that gives us 731642. 731642, yep, matches up with D. So nice and quick for that question. Which matrix products are defined? So this is similar to the question that we had before about sort of deciding when matrices are defined. So let's check out, again, let's use trial and error. So let's check out, is A, B going to be defined? A has 2 columns and B has 3 rows. So if you wanted to just sort of write them out, AB would be a 2 by 2 matrix multiplied by a 3 by 1 matrix. AB is not defined because the 2 middle numbers aren't the same. So option A is not going to be it. Let's see, is AD defined? So A is a 2 by 2 matrix and D is also a 2 by 2 matrix. So AD is defined. Let's see if AC is defined. 2 by 2 and C is a 3 by 3. So nope, AC not defined. It's not going to be option B. Let's try option C. Let's try, is CB going to be defined? C is a 3 by 3 and B is a 3 by 1. So yep, CB is good. Is BC good? 3 by 1 matrix multiplied by a 3 by 3 matrix. So nope, middle numbers not the same. BC is not defined. Let's move on to option D. Is BD defined? B is a 3 by 1 matrix and D is a 2 by 2 matrix. So nope, BD is not defined. That leaves E. So let's just double check we've done this correctly. We already know that AD is defined. So let's check, is DA defined? DA is 2 by 2 multiplied by another 2 by 2 matrix. So yeah, DA and AD are defined, meaning our answer is option E. We've got this matrix P, and this is sort of that the element rules questions. So we've got the element in row I and column J is Pij. So for example, this one is in row 2, column 2. So this would be labeled as P22. So the elements in matrix P are defined by which rule? Probably best to continue trying to use trial and error here as well. So let's try A. So 4 minus J. J is the columns. So 4 minus column 1 is 3. Yep, that works. 4 minus 2 is 2. 4 minus 3 is 1. All right, so we're good for these ones. And then if we look here, this is still column 1. So this would be 4 minus 1, which is 3 again. So A is broken. Let's try B. 2i plus 1. If we jump straight to this element here, this is in row 1. So that's when I is equal to 1. So 2 times 1 plus 1 is 3. We can straight away see that breaks for that one. Let's try C. It's I plus J plus 1. Let's try this very last element, because we know that I and J are going to be quite large. I is 2, and J is 3. So 2 plus 3 plus 1 is 6, which does not equal 3. So C is broken. D is I plus 2J. Again, I'll focus on this last element because I and J are large. So again, I is 2 and J is 3. So 2 plus 2 times 3, which is 6. 2 plus 6 is 8. That breaks to 3. So we've shown that A to D are broken, and E is the only one that remains. Let's just check a couple of them to make sure E works. Let's again focus on this last one where I is 2 and J is 3. 2 times 2 is 4, minus 3 is 1, plus 2 is 3. So that works. Let's try this one. I is 2 and J is 1. So 2 times 2 is 4, minus 1 is 3, plus 2 is 5. And you could keep checking the rest if you want, but I'm fairly satisfied that E is the only one that works here. The matrix Sn plus 1 is determined from the matrix Sn using the rule Sn plus 1 is equal to the transition matrix T multiplied by Sn minus C. And we've got our T matrix, our initial state matrix, and the C matrix here. So given this information, we want to find S2. So the key piece of information here, we've got this general rule here. Let's see where this comes up in our notes. We've got our matrix modeling when using Sn plus 1 is equal to Tsn plus B. So it's in that sort of form. Now, if we look up, if we sort of scan through our notes, we'll say that there is no easy rule to find the nth step. So if you're trying to find S2, 3, or 4, you actually need to go step by step. So you need to sort of use the rule to find S1, and then use the rule again to find S2. So we're going to have to do that in our calculator. First thing I'm going to do is I'm going to define each of my matrices, as that's going to save me time in the long run. I've got all my variables in there. Now let's get S1. So S1 will be T multiplied by S0 minus C. All right, so that is our S1 matrix. And I might just quickly define that as S1. You don't have to define it if you don't want. I just find that putting that in my calculator looks a bit nicer than using matrices everywhere. So now I'm just going to use S1, and that will give me S2. So a column matrix with 148 and 122, thankfully that matches up with an option we've got here, so I'm pretty confident that's correct. So B. Stella completed a multiple choice test that had 10 questions. You had five possible answers A to E. For question 1, Stella chose E. Stella chose each of the 9 remaining questions in order by following the transition matrix below. So this is our transition matrix. We're going from this question to the next question. We want to see, what did Stella choose for question 6? So let's just sort of go step by step. So we know she started with E. So that's question 1. So because she chose E for this question, maybe just to keep track, we'll write them down as well. So 1 was E. The next question was C. So because the next question was C, we'll look at C and move down. We know the next question after C was A. Then after A, the next question was D. After D, it was B. And finally, question 6, after B, we're back to question E. And it would start to repeat after that. So E was question 6. Now we want to know which one of these has a determinant of 0. Now, I'm just going to use the calculator for that one. Remembering that we can calculate determinants using this DET function. So that's not it. That one's not it. Not C. Yep, and we've got D. So D has a determinant of 0. Which of the following matrix equations has no unique solution? So again, this is actually another determinant question. Remember that you have no unique... Oh, sorry, we're looking for ones that do have a unique solution. So remember that you have a unique solution if the determinant does not equal 0. So in this case, we're looking for matrices whose determinants are not 0. So again, let's just keep doing determinants. So A has a determinant of 0. So that has no solutions. Again, B has a determinant of 0, so no solutions there. And we see that C has a non-zero determinant. Therefore, C will have a unique solution. So this table below shows the number of each type of coin saved in a money box. The matrix product that displays the total number of coins and the total value of these coins is what? So because we're looking for two values, we want the total number of coins and the total value. We know it's going to need to be a matrix that has at least two elements. If you think about this matrix product, this is going to form a 1 by 1 matrix when you multiply these together. Now, the way I like to sort of think of it in my head, the way I know that just by looking at it, is it's kind of that intersection rule that we looked at in the way I sort of set it up in my head. So maybe if I get that there. So when I see this matrix multiplied by this matrix in my head, I just kind of slide this matrix up a little bit so that it looks like that. And I know that the lower right intersection of those matrices is going to be the order of the product. You can think about, if you sort of slide this one up, the intersection is just going to be this little 1 by 1 square. So straight away by looking at it, I know A is not going to be the answer. I know D is not going to be the answer. But B, C, and E are all going to have matrices that have at least two elements. So it could be any of them for now. I know the answer is B, and I'll explain why. If you think about what this matrix multiplication is actually doing, you're taking 15 times 1. So let's say it's going to be a 2 by 2 a 1x2 matrix product, this one, and it's going to be in the first element, it's 15 times 1 plus 32 times 1 plus 48 times 1 plus 24 times 1. So the first element, it's just adding up these numbers. That's all it's doing. And if you think about it, these numbers added up is the same as the number of coins that there are in total. So already our first element gives us the total number of coins. So that's the first thing we wanted. The second thing we want is the total value of these coins. Let's think about what the second element in this product will be. You're taking 15 times 5 plus 32 times 10 plus 48 times 20 and then 24 times 50. What that's doing is it's saying you have 15 5-cent coins. So if you want to work out the value of 15 5-cent coins, you're obviously going to multiply 15 by 5, which is what's happening here. You're going 15 times 5. Then you're adding 32 10-cent coins here. Then you're adding 48 20-cent coins and 24 50-cent coins. So the second element in this matrix product will be the total value of the coins. So that's how we're thinking the answer is option B. And this is our last multiple choice question. So Kai has a part-time job. Each week he earns money and saves some of his money. The matrix below shows the amounts that he earned, which is E, and the amount he saved, S, in dollars for 3 weeks. How much did Kai save in week 2? So this question is just asking you to simply interpret the matrix that we've got here. So we've got some information in a matrix and we want to understand what's going on. So we know in week 2 is this row number 2, and the money he saved is denoted with this letter S, which is in column 2. So if you look at the intersection of the savings and week 2, it's this 90. So he saved $90, which is option B.